let's look at some derivatives that we've learned so far. We learned that the derivative of e to the x is just itself, but that if that exponent is a function, then I do need to go ahead and multiply by the derivative of the function and then my e to whatever that function is. So kind of a chain rule going on here. That the derivative of natural log of x is 1 over x, but same situation, if that is really a function in the argument, then I need to multiply by the derivative, and then I still have that 1 over the function going on. And then the last one is more of a specific case, that if I'm looking for the derivative of the inverse at a specific value, that I can use this 1 over the derivative of the inverse of that value. For all of these functions, we have a base of e. So whether we're talking about an exponential or a log, the bases were always e. So what we're going to add in today is what a derivative looks like if we have an exponential or a logarithmic situation, but the base is not e. So for each of these derivatives, we're going to let a be a real number such that a is not 1. We're dealing with exponentials, logarithms, so we don't want that base to be 1. That's going to mess up what we're doing. But for our first derivative, we're going to look at an exponential situation where instead of having a base of e, we've got a number raised to the x. And notice that this is going to be really similar to our e to the x, where it just is itself. But because we don't have that base of e, there has to be something to kind of correct that. So our derivative is going to be that a to the x, but then times the natural log of a. But for each one of these, we're still going to have the case where we've got just x, and then a case where we've got more of a function that we're going to use u to replace. So if we don't have just a to the x and we've got a to the u, the only difference here is we're still going to have that a to the u times the natural log of a to fix the fact that we don't have a base of e, but then we're just multiplying by u prime at the end. So very similar to these two. The only difference here is that we're multiplying by that natural log of a. Okay, for the derivatives of logs, so if we have a log base a of x, again, going to be really similar to this situation. We're going to still have that 1 over x in our derivative, but then kind of to correct the fact that we don't have a base of e, we're going to multiply by 1 over the natural log of a. And if you remember from pre-calc or from Honors Algebra 3, this comes straight from the change of base formula. So this is kind of extra. If it doesn't make sense, throw it out, but I think it's pretty neat. If we were to take log base a of x, I'm allowed to rewrite it using the change of base formula, which I can use any base for, and I can just rewrite it as log base whatever of x divided by log base whatever of a. So if I use a base of e, that means I could write it as natural log of x divided by natural log of a. Then when I go to take the derivative, my derivative of the natural log of x is my 1 over x. And then this 1 over natural log of a is just a number. So I don't have to use the quotient rule here because this isn't a function, because remember a is a number. So the natural log of a is also a number. So this is just kind of that coefficient that hangs out on the outside of the derivative. So we've got the derivative of natural log of x, and then just times that coefficient that's left over. So kind of neat to see where that came from. And then our last one, if we have a u here instead of just x, the only difference being that we're going to have that u prime over u, and then still having to multiply by the 1 over natural log of a. So really the only difference here in our base e's and base some other number is the fact that for exponentials I need to multiply by the natural log of a, and then for logarithms I need to multiply by 1 over the natural log of a. So for our first example, we've got the derivative of x times 9 to the x. So first, just recognizing that it is multiplication, we're going to have to use the product rule. So I'm taking the derivative of x, so 1 times 9 to the x, plus my derivative of 9 to the x. So just recognizing, okay, I've got that exponential, but without a base of e. So remember, it's going to be that 9 to the x, but then times the natural log of 9. And then normally if this was a different function, I would have times the derivative of x, but I don't need to do that. So just to clean it up a little bit, multiply some things out. And then kind of depending on what you're doing, maybe we would want to factor out the 9 to the x. Because this right here is really a number, so we might want to get it by itself, I don't know. So for our second example, we've got the derivative of a log, and we might notice right off the bat that it looks like we might have to end up using the quotient rule, because if we do have a log, we're taking the derivative, we're going to end up with that u prime over u at some point, and I really don't want to use the quotient rule if I don't have to. So something we're recalling about logs is that we are allowed to expand them if they have that multiplication or division in the argument. So since I have division here, I'm going to expand it into log base 2 of x squared minus log base 2 of x minus 1. And with this first one, we could move the 2 out front, but it's not really going to be any more simple that way, so I'm just going to leave it. So now when I'm taking the derivative of this first log, I'm just going to have that derivative of x squared over x squared. And then remember, because I don't have a base of e, I've got to multiply by 1 over the natural log of 2. Similar for the second log, I'm going to have the derivative of x minus 1, so just 1 over x minus 1 times that 1 over natural log of 2. Now, if you're doing the homework from Delta Math, I don't think there's anything even this complicated. So I don't know that you're going to run into simplifying issues, but if you're using the textbook, they are simplifying to where everything is one fraction. So we can simplify our x's over here. We'll get rid of one of those x's and the one in the denominator. But then from here, they both have that natural log in the denominator, but this one has an x and that one has an x minus 1. So just getting a common denominator by multiplying this fraction over here by x over x. We're going to multiply this fraction over here by x minus 1 over x minus 1. So that we just have this large fraction. No matter what order we're in here. And then in the numerator, we're going to have this 2x minus 2. And then minus x. So an x minus 2 over, I guess you could distribute that x, I don't know. It's kind of hard to know what the back of the book is going to do sometimes, if they're going to continue simplifying or not. But something like that, where you have one fraction. Now, when you're not working with the textbook, as long as you can do this first step of just expanding it, taking the derivative, that's really what we're focused on. But as far as being able to check it, so the only new information that we need when integrating is just that the integral of a to the x. So if we have any base here, again, that a not being 1, our integral is going to end up being a to the x times 1 over the natural log of a. And then anything else that we're integrating, we're going to be using u substitution and then just the antiderivative of derivatives that we've learned so far today. So if we have something as simple as the integral of 2 to the x dx, we're just going to be using this integral up here and saying, okay, that's going to be 2 to the x times 1 over the natural log of 2 plus c. If we have something a little more complicated, now we're looking to use substitution. Because this does have an exponential in it, I'm still looking for this to happen. So I'm looking to have that exponential to where I can use this integral. We're just not quite there yet. So thinking through my u substitution, nothing has changed here. I'm still trying to pick a u that the derivative is also there. So I want to choose this negative x squared because it's stuck in the exponent, but also because when I take the derivative, I'm going to end up with something that has an x to the first in it. And I know that I can make that happen. I already have an x to the first in my problem. But I do need that negative 2, so I'm going to be multiplying by a 1 over negative 2 and a negative 2. So I've got this negative 2x dx, that's all going to go into my du, and then I've got the integral of 5 to the u. So at this point, my problem looks like the one before it did, aside from the fact that I've got u instead of x, and that's okay. So I'm going to have a negative 1/2 my 5 to the u times 1 over the natural log of 5 plus c. And then at the end here, I'm just going to put my negative x squared back in for my u. There we are. My last example is a rational function, and remember that if we can get this to look like 1 over u, then I can integrate and have natural logs involved. So we are going to have to use u substitution, but looking to make possibly that entire denominator the u. And then we'll just see what happens here. My du, taking the derivative of this, I've got my 3 to the 2x, just like e to the x. But then remember, I've got times the natural log of the base, and then also times the derivative of 2x. So my du is a little lengthy. I have parts of this already. I already have my 3 to the 2x, but I am missing the natural log of 3 and the 2, which is not really a big deal because this is a number. So I'm allowed to multiply by natural log of 3 times 2 over natural log of 3 times 2. In fact, I'm going to go ahead and make it 2 natural log 3. So now we have that whole numerator and the dx that is going to be absorbed into the du. So we've got the integral of 1 over u du. So we did end up with that 1 over u. And then our integral of 1 over u is going to be the natural log of the absolute value of u. And then at the end here, just plugging back in our u. Plus c. We're going to end today with an application problem. This is number 108 from your textbook on the lesson 5.5. So it says, in a group project in learning theory, a mathematical model for the proportion p of correct responses after n trials was found to be this equation. And so for any free response question that gives you an equation like this, we want to make sense out of what that domain and range are. What exactly are they plugging in? What exactly are they getting out of it? Are they talking about a rate? So did they give us a derivative, or did they give us the original function? So making some sense out of this, it says n is the amount of trials that have happened. So say they've had 10 trials, so they're plugging in 10 for n. The thing that they're getting out of it is the proportion p of correct responses. So kind of giving yourself an example, if we had 10 trials and they were correct 5 out of 10 times, that means that if I plug in 10, I should get out 0.5 or 1/2 for the proportion of correct responses being 5 to 10. Of course, the 5 to 10 was just made up. I was curious, and so I went ahead and plugged in 10 for the number of trials, and for your proportion, you get out 0.79. So after 10 trials, they're correct 79% of the time, which it actually keeps going up, but it's going to level off at some point. So looking at part A here, they want us to find the limiting proportion of correct responses as n approaches infinity, which is really just a fancy way of saying what is the limit as n approaches infinity of this function. Is that proportion going to level off at some point? It can't go off to infinity because it is a percentage, so the greatest it could be is 1 anyway. And we might notice for something like this, we might be thinking L'Hopital's rule, But remember, for L'Hopital's, I have to plug in infinity and get, well, plug in whatever I've got here, and get something indeterminate. So it'd have to be an infinity over infinity or a 0 over 0, and that doesn't happen when I plug in infinity. So what I want to do is either plug in some values to kind of see what's going to happen here, or to just focus on that piece that I'm going to actually be plugging into and see what happens with that. Because for this little piece right here, I've got e raised to a negative power. So really I have 1 over e to a power. So as I plug in higher and higher values of n, what's going to happen to this, since it is a fraction and the denominator is getting larger and larger, this whole piece right here, as n goes to infinity, is going to go to 0, because I'm going to have 1 over e to the 0.25. If I plug in 2, I've got 1 over e to the 0.5, which is larger. So it's just going to get bigger and bigger in the denominator. So kind of a bigger on bottom situation where this is going to go to 0. So that means that my whole limit is going to go to 0.86 over 1, or 0.86. And if you plug in larger and larger values of n, you should get the same thing. In fact, your calculator, it will be so close to 0.86 that if you plug in, I think it was 100 trials that I plugged in, for n, it should just tell you 0.86 is what it limits to. For part B, it's wanting to know the rates at which p is changing after n equals 3 trials and then after n equals 10 trials. So the important part here being the rates, that's what we're looking for. So going back to what they gave us, we're trying to decide, is what they gave us a rate? And it is not. We're getting out the proportion of correct responses. It is not the rate of the correct proportion responses. So before I plug in my 3 or my 10, I'm going to be finding the derivative of this. So my first objective is to find p prime. But first I'm going to put my equation in a form that's going to help us out here. So if I'm finding the derivative of this, I'm going to go ahead and move everything in the denominator up to that numerator. It is all grouped together, so you're going to have this whole 1 plus e to the negative 0.25n, all raised to the negative first, since I moved it from the denominator to the numerator. And now I can go ahead and find p prime just using the power rule. So I've got a negative 0.86. I'm going to have this 1 plus e to the negative 0.25n, now raised to the negative second, so that was my power rule. But now using the chain rule, so I did the power and then now the derivative of the inside. So my derivative of e to the negative 0.25n is e to the negative 0.25n times the derivative of the exponent, so times negative 0.25. Whew. Okay, so this is not super pretty, but you would have a calculator to plug this into. Even if you didn't have a graphing calculator, we're just plugging in a value, so we shouldn't have too much trouble. You might clean up some things here if you wanted to go ahead and multiply negative 0.86 and negative 0.25, go for it. But we're just finding p prime of 3 and p prime of 10 from here. So just plugging them in. We should get 0.047 for p prime of 3 and 0.015 for p prime of 10. So what this is saying is that it's increasing at a rate of 4.7% per question. So after 3 questions, if we plugged it into the original, we could get that proportion, but this is telling us that at this point, that proportion is increasing 4.7% per question. And it makes sense that the more questions you do, the less it would be increasing, because we know that it levels off at 86%. So for p prime of 10, it's increasing at a rate of 1.5% per question. So because this levels off, eventually it'll be so close to the derivative is going to be like 0.000, you know, almost 0% increase, because it's got to level off at some point. Or I guess the word that they used here was trial, so we should use their word. I don't know that they're asking them questions. I was given very little information about this project, okay?